Good afternoon, everyone. I'm excited to share with you the physics which lies at the heart of my research and which demonstrates some fascinating quantum features. I'm talking today about superradiance, a quantum mechanical effect that occurs in groups of molecules where each member, if it were considered in isolation, would be capable of photon emission via a quantum energy level transition. I'll show how a collection of such molecules can radiate with incredible intensity, an intensity which betrays the presence of some amazing inner quantum workings, including entanglement and superposition, and an intensity which is greater than the sum of the group's individual parts. What's also exciting is that this is a very real and very measurable effect. It demonstrates quantum strangeness that we might think should be relegated to simple, idealized thought experiments. Not so. Superradiance shows up in the lab, and it shows up in astronomical data. Serge Haroche, a French physicist, used it in his development of new methods of laser spectroscopy, which won him the Nobel Prize in 2012. So my talk is not just a description of superradiance, but an exploration of why the phenomenon is so remarkable. I'm going to spend some time motivating and then driving home this take-home message that seeing superradiance is as amazing as seeing something in two places at the same time. But I've skipped to the punchline, so let me step back a bit. We're all familiar with quantum mechanics, but I'd like to provide a refresher on some subtle points about superpositions and information describing a quantum state. These points will help us appreciate superradiance better in a moment. So here's where we're going. First, I'll provide a quick refresher on what it means to be in a superposition state.
Thinking about quitting smoking?
Then I'll give a concrete example with a position observable in quantum mechanics, pardon this commercial that's on.
$500. If you quit for the first week, you're 9 times more likely to quit for good. Register at firstweekchallengecontest.
Back to the music. Then I'll give a concrete example with a position observable in quantum mechanics. And I'll highlight key takeaway points from the example which will build our intuition for the quantum strangeness of superradiance. Then after this quick quantum refresher, I'll describe superradiance proper. So consider first the position observable of a particle. Classically, this property is uniquely defined. If a particle is at A, then it is not at B, and vice versa. But in quantum mechanics, the particle may assume more rich states of existence, such as the state of being simultaneously at A and at B. We say that the state of the particle is equal to the state of being at position A superimposed with the state of being at B. Okay, fine, nothing new. We all know what this means. But to the clever early student, an operational question immediately arises. What good is it to say that the particle is in two places at once? When and how does this statement assume any real meaning? I could respond, well, the results of subsequent probing of the particle's position give the superposition its meaning. After preparing a system in the superimposed state and asking where it is located many times, we obtain a statistical distribution of results consistent with the superposition state. 50% of the time the particle is measured at A and the other 50% of the time at B. But my answer is somewhat unhelpful and unsatisfactory to a clever student who follows up with, why can we not simply say that the preparation of the system is statistical? That half the time the particle is prepared at A and the other half of the time at B, and that what we are calling a superposition is actually nothing more than an uncertainty in our knowledge of the experiment's preparation. Responding to this question gets to the crux of quantum mechanics. I would reply to this student, in this isolated sense, you have a point. If the universe were nothing more than this simple experiment in which a particle is in the state A superimposed with B and we probed its location repeatedly, then the superposition description would be indistinguishable from the statistical preparation description in which the particle is prepared at A half of the time and at B the other half of the time. However, when we try to formulate a physical theory of the system's evolution and interaction with an environment, we find that it becomes absolutely logically necessary to describe the particle state as a superposition. We find that, in fact, the two constituent states of the superimposed state interfere with each other and yield further results which are intractable with any classical theory of a statistical preparation to the system. Let me clarify with an example. Consider the double slit experiment. A particle is first placed in a superposition state of simultaneously existing in two places. It is then left to evolve, and its position is again measured at a later time. Any classical attempt to build a theory describing this experiment would first formulate a theory for the particle passing through slit A alone with slit B covered, then through slit B alone with slit A covered. And the final theory describing both slits would of course be the statistical sum of each independent sub-experiment. But incredibly, the two-slit experiment results cannot be drawn into consistency with independent sub-theories of particle propagation through each Ingles slit individually and separately. Instead, the significance of the superposition state is forced upon us. As the superposition state evolves, the evolution law for the state of passing through slit A interferes with the evolution law for the state of passing through slit B, and the final result is an interference pattern of final position measurements which is not the statistical sum of the sub-experiments. So we see here that the fascinating and classically forbidden features of a quantum superposition appear not in measurements of that state in isolation, but in the rich results of subsequent evolution and interactions. And these results are completely incompatible with classical thinking. Or, you cannot directly observe a superposition, but you can observe subsequent results which cannot be logically reconciled with any classical understanding. And we'll see this in Superradiance in a moment. This is a subtle point, but I believe it's important to gaining an intuition for how the superposition state rears its strange head in any quantum system. I'd like to make a second observation here on the double slit experiment, which will also help us appreciate the otherworldliness of superradiance. What's truly remarkable is that when we shifted from a quantum description of each individual slit separately to a quantum description of both concurrently, we did not introduce any physical interaction between the two slits. We only removed information from our description of the problem. We lifted our knowledge of which slit the particle passed through, and that lack of knowledge introduced the exotic interference pattern. Suppose, alternatively, that we had added a sensor to each slit and labeled each particle detected at the final screen with which slit it had passed through. The quantum formalism to describe this new experiment is straightforward and, incredibly, shows that the entire interference pattern disappears. This brings me to my second point. Exotic quantum features or interference patterns can be destroyed simply by associating the information of a substate in a superposition with some other observable. So let's turn now to superradiance, where I'll stress the importance of the superposition state and of the information we use to describe the system. Let's build up a superradiance system. Consider one molecule which can exist in two different energy eigenstates, call them the ground state and the excited state. In perfect isolation, this molecule would remain in either state indefinitely. Formally, the Hamiltonian operator on this isolated system has been diagonalized, and Schrodinger's equation dictates that an initial state excited remains excited forever. But no system can truly exist in complete isolation. In fact, the single molecule interacts with the very background vacuum itself. The molecule possesses a dipole charge distribution, and the quantum mechanical dipole moment operator interacts with the quantized electromagnetic field of the background vacuum state. This interaction produces a perturbation to the Hamiltonian operator and couples the excited and ground states of the molecule. The molecule vacuum compound system time evolution now includes transitions between the excited and ground states with accompanying production of a single quanta of the electromagnetic field, a photon, or as I've shown here, the transition from the state of being excited with no photon present to the state of being in the ground state with a photon present. After performing a detailed quantum electrodynamic calculation for the expectation value of photon emission, we eventually obtained the Dirac formula, which describes the probability per unit time for a single molecule with dipole moment d to decay and emit a photon. Omega naught here is proportional to the energy difference between the excited and ground states. The gamma probability of photon emission allows us to calculate the effective average power radiated by an individual molecule. It'll look something like this, a typical exponential decay. But now things start to get interesting. Suppose we double the size of our system. We add another molecule, but we do not allow the two molecules to interact in any way. According to classical statistics, we expect to see twice the radiation intensity. Twice the molecules radiating per unit time, twice the radiation, right? Well, if we set things up crudely, that's what we'll see. Pretty boring. If we place one molecule in one location, and the second a fair distance away, such that a radiated photon can be definitively identified with its source molecule, then yes, the power just doubles. This is a reflection of the limitation of quantum states available in our description of the system. Because we identified each photon detection event with a specific generating molecule, we're effectively restricting transitions to occur between the states shown here. For instance, from the EG state, where we know with certainty that the first molecule is in the E excited state, and the second molecule is in the G ground state, to the GG state, where we know with certainty that it was the first molecule who transitioned to the ground state. Now, however, suppose we place the two molecules very near each other, such that they are separated by much less than the wavelength of the photon that they emit, and we are no longer able to identify which molecule a received photon has been generated from. We haven't even introduced an interaction energy between the two molecules, we've simply removed information from our description of the system. This is analogous to the double slit experiment we saw earlier, where we allowed the electron to pass through both slits, but we did not ask which slit in particular it passed through. Now we allow the system to radiate, but we don't ask which molecule radiates. Suddenly, the system is drastically different. We never ask who produced the photon, and by doing so, we allow the system to exist in new, rich superposition states. Namely, the system can now exist in the simultaneous superposition of GE and EG, where the first molecule is in the ground state and the second excited, and simultaneously the first molecule is excited and the second in the ground state. This state presents a new time evolution avenue for the system. The system may now start in the state EE and transition through S to GG. This is fascinating. It's as if two narratives are unfolding simultaneously, as if the story of molecule A emitting first, then molecule B emitting second, is happening simultaneously with the story of molecule B emitting first and molecule A second. When we compute the time evolution of the system with the formalism of quantum mechanics, we obtain the modified power transient behavior. And this is the amazing feature of superradiance. By simply treating the ensemble of molecules as one quantum system, without introducing any interaction between its members, we realize enhanced radiation. For two molecules, the effective power transient is only slightly modified, as you see here. But for 10 molecules, the response is dramatic. The superradiant prediction matches the initial power of the classically expected radiating group of 10 molecules, but peaks with incredible intensity after a short delay time, and decays faster than the classical response thereafter.